everyone, and welcome to the high voltage seminar. And then the topic of this session is using the SiC MOSFET in the auxiliary power supply, presented by Sutesh. And before beginning, I have some quick notes here. First, all participants are muted for these sessions, so please use the chat function to ask the questions. And then after the presentation, we'll address this question and to everyone. And then if you want to send them questions earlier, it'll be great because I can compare these questions and then bring this question to the presenter. And then secondly, allow me to introduce the presenter. The stage is the system engineer in high voltage controller group in TI, and he received PhD in the electrical engineering from in the Indian Institute of Technology in 2015, and he was also a visiting scholar in the Colorado Power Electronics Center at the University of Colorado Boulder. And before joining TI, he had 5 years experience on defining the power management products for automotive and LED driver applications. With that, I will hand it over to a stage to get started.
Thanks, Patient. Good morning, everyone. Welcome to this session on driving SiC MOSFETs and auxiliary power supplies. So here is the content of the session. We'll briefly discuss the various end equipment with their block diagrams in high voltage bias power applications. And the next is we'll discuss what are the candidate topologies in these high voltage aux power or bias, auxiliary or bias power supplies, and the design considerations for driving silicon carbide based flyback converters, and finally the summary. Okay, before jumping into the topic, since silicon carbide is the device of interest, a quick overview of the silicon carbide device. As you know, silicon carbide is one of the wide bandgap devices, and here we are showing different properties, very important properties of silicon, GaN, and silicon carbide materials. Firstly, the bandgap energy of a silicon carbide is much higher than the silicon, and the breakdown field strengths, these are also much higher than the traditional silicon and on par with GaN, and saturation velocity is much higher than silicon, and electron mobility, although less than silicon and GaN, and finally the thermal conductivity, which is much higher than existing silicon and GaN materials. Then how does these properties translate into system benefits? Firstly, the high bandgap energy and high breakdown voltages leads to a high voltage operation for the silicon carbide. These devices can be operated at very high voltage and even at very high temperatures. And the high velocity saturation, although low electron mobility, the high velocity saturation helps the silicon carbide to turn on and turn off faster, and thus lower switching losses. The lower switching losses in turn will allow the power switches in the system to operate at high switching frequency, which will help to reduce the filter sizes, filters and passives like inductors and capacitors. And finally, the high thermal conductivity helps in reducing the cooling needs in these power systems. All these advantages would lead to a lower size of the system, of the power system, and lower cost and weight. And these are the main benefits of moving to a wide bandgap device like silicon carbide. Okay, having a brief overview of the silicon carbide, let's see what are the applications for this silicon carbide MOSFETs in auxiliary power supplies. So one of such application is a central PV inverter. Typically, the central PV inverters are used in all large-scale utility solar power plants, as well as large commercial solar plants. And in these solar plants, in order to power the auxiliary power needs like gate drivers and the signal chains and microcontrollers, to power all these additional electronic equipment, a flyback converter would be used. And this flyback converter being shown here, in this PV inverter architecture, typically two flyback converters would be used. One of them would be driving from directly the PV voltage, the DC bus coming from the solar PV panels, and the other flyback converter would be driven from the grid side. So there is a need for two flyback converters, because during night times, when there is no power input from the PV, the flyback converter coming from the grid side would supply the power to the auxiliary bus, DC bus. Now, what is the need for high VDS rating of the silicon carbide here in these flyback converters? It's mainly being driven by this high DC bus voltage of the PV panels, particularly in a large scale utility PV inverters. This input voltage range can be from 1000 to 1500 volt DC. With such high VDS ratings, silicon carbide is the only solution with a single switch flyback converter topology. And another use case for the auxiliary power supplies is electricity meters. Again, in electricity meters, a silicon carbide based flyback converter is being used more popularly these days because of the high operating input voltage range, as high as 950 volt DC, particularly in polyphase and electricity meters. Again, the main motivation for using the silicon carbide is higher VDS ratings. And another application use case is AC motor drives. So here is the block diagram of the AC motor drive. Again, in order to meet the DC voltage requirements of electronic loads and the gate driver power supplies of the main inverter driving the AC motor, this auxiliary power supply is realized using a flyback converter. And typically for a for a polyphase or a three-phase AC system, the input voltage range can be very wide, from 300 volt to 1100 volt. So in order to accommodate such a high DC bus voltage ratings, a silicon carbide based flyback converter is being employed. And another advantage of this SiC based, another requirement of this SiC based flyback converter in this application is the removal of heatsink, which would minimize the space required for this bias power supplies or aux power supply in this system. The typical power levels are 20 watt to 60 watt. So here is another use case, which is a auxiliary, or also called as redundant power supply in traction inverters of electric vehicles. So in electric vehicles, typically there will be two batteries. One is a low voltage battery, a 12 volt battery, and the main battery, which is a 400 volt or 800 volt, is the main battery which is used for driving the traction inverter. And in this traction inverter, again, in order to supply the gate drive power for these IGBTs or silicon carbide based MOSFETs in this traction inverter, there is a need for bias power. And that bias power is typically generated through either this 12 volt DC bus directly, or there is an additional redundant power supply, which is a flyback converter, which will be ORed with this 12 volt supply. The need for this redundant bias supply is the safety considerations while designing the traction inverter. So in the events of a non-availability of this 12 volt rail, the high voltage battery can provide the bias power for this traction inverter. And typically, again, the operating input voltage range for this flyback converter is very wide, from 50 volt to 1000 volt for a 800 volt battery system. And with such high DC bus voltage, with such a high battery voltage, higher radius rated MOSFETs are required, and that's why SiC is a preferred switch in this solution as well. Also, the another requirement in this system is a high efficiency. Although the previous slide we have shown the generic configuration for a oxide power supply in traction inverter, there can be different configurations basing on the OEM's choice. Here we are showing such 4 cases. In first case, you could see here all the gate drive bias power is being generated from 12 volt battery as a primary bias power source, and this silicon carbide based flyback is being used as a backup source for all these rails. So this is one case. And in the second case, all the high side switches of the traction inverter are being driven from the 12 volt battery, the bias power from the 12 volt battery, and all the lower switches are being driven from the bias power from the high voltage battery, as well as this silicon carbide flyback would also serve as a backup for the high voltage bias power. And in case 3, all the switches, high side switches and low side switches, are being driven primarily from the high voltage battery through this SiC flyback, and the 12 volt battery would be functioning as a backup. The fourth case, finally, is all of these high side drivers and low side drivers are being again driven from the silicon carbide based flybacks, and this case is still not in the all OEMs are not implementing this stage. This is still in exploration stage, but the case 1 and case 2 are more commonly found in typical OEM applications. Okay, so we have seen different use cases for silicon carbide based aux power supplies, and let us see the main topology which is being used in these use cases, which is a flyback. So yes, flyback is the main topology which is being used in all these applications. But if basing on the silicon based flyback converter has to be used in these applications, the regular single switch flyback is not suitable, because the silicon MOSFETs are not available all the way up to 1700 volt rating VDS. So that's why cascaded flyback is the alternative solution when a silicon switch is being used in such high voltage flyback applications. So on left, you're seeing this cascaded flyback using two silicon switches with a low voltage rating, which is a 700 to 800 volt rating, and realizing 1700 volt overall VDS rating. On the right, if a single switch solution can also be preferred alternative when using a silicon carbide switch, because silicon carbide has a higher VDS rating up to 1700 volt. Now, comparing the performance of these two solutions, one is silicon-based cascaded flyback with the silicon carbide-based flyback. Here is the performance summary. With the cascaded silicon flyback, assuming two 900 volt switches from this Infineon, these are the power loss distribution: connection loss, turn on loss, gate drive, and the total loss is 1.62 watt. Whereas with the silicon carbide switch from the ROM, 1700 volt, one switch would be sufficient, and the total power loss is 1.3 volt. Obviously, the power loss with silicon carbide single switch based flyback is less because of the lower radius on of the because of the only one switch, which is 1.2 ohm, is the radius on in this system, whereas in this system we have two switches of 1.2 volts, and also we have two switches which are which needs to be switched. The switching losses also would be doubled. So that is the reason why you would see more loss in the silicon flyback. One assumption in this analysis is both the converters in this case are being operated in a DCM mode. Okay, so we already, TA has a reference design TDA for up to 690 volt AC input for a 50 watt flyback isolated power supply reference. You would see two silicon based MOSFETs here, and also the associated clamp circuitry for this high side silicon switch here is being highlighted. So this is the additional circuitry that is required when using a silicon based cascade power supply. On the right, you could see this additional components that is being placed on the PCB as well, and the additional heat sinks for this device as well. So all the heat sinks, additional components would increase the space and also would decrease the reliability of the solution. So here is the cost performance, cost comparison for both cascaded flyback and flyback. Since there is no need for additional switch, there is no need for all the clamping circuitry related to that additional switch, and also no need for additional heatsink. The total switch solution cost with this silicon carbide flyback is lesser than the two switch cascaded silicon flyback. So TA also has a flyback reference design for 800 volt battery system based traction inverter. This is a TDA 01505, which uses a silicon carbide switch with operating input voltage range from 40 volt to 1000 volt VIN. Okay, a little bit about this TDA reference design. This TDA reference design uses our TI's UCC28C43 general purpose PWM controller, and along with some additional external circuitry, this flyback power supply will be able to meet the needs of SiC-based redundant power supply in the traction inverter. I'm not going through these details. These all are available in this reference design. But here I'm just showing the experimental results of this design with SiC-based flyback. So startups and shutdowns typically are very important in these redundant power supplies, as well as the low transient response. And you can see the efficiencies, measured efficiencies, all the way up to 1000 volt VIN. Okay, now we have seen the main use cases or application use cases for this silicon carbide based aux power supplies, and what are the advantages of this SiC based aux power supply compared to a silicon based cascoded flyback topology. Let's get into a deep understanding of the design considerations for driving SiC based flyback aux power supply. Okay, so there are several options in order to drive these flyback converters through TI's general purpose PWM controller portfolio. At the extreme right, you could see the UC284 series and these are TL284 series. These are bipolar general purpose PWM controllers, which can be used to drive the flyback converters. And on the left, you could see the BiCMOS based high performance general purpose PWM controllers. So there is a huge product portfolio, and depending on the needs of the application, a suitable controller can be chosen. So here is one of the aux power supplies reference design using our UCC X8C4Y family PWM controller, which is UCC28C42. So in this case, here it is driving a silicon MOSFET, and there are additional external components for additional features such as soft start and the slope compensation. And in this case, an optocoupler is being used to get a isolated feedback from the secondary side through a TL431 reference. This is a very standard flyback aux power supply design using this UCC28C42. Here you can notice that UCC28C42 can be directly used to drive the silicon MOSFET without any issue, because this PWM controller is designed to drive the silicon MOSFETs, which means the output voltages of the output voltage of this PWM controller, which is again dependent on the VDD, which is a maximum of 18 volt for this PWM controller, is suitable enough to drive the silicon MOSFET directly. No additional circuitry is needed when driving a silicon MOSFET between the PWM controller and the silicon MOSFET. Now, what are the PWM controller requirements for driving a silicon carbide MOSFET? So in the previous slide, as I've been telling, this controller is suitable to drive the silicon MOSFET, but it is not suitable to drive the silicon MOSFET. So now let us understand what are those requirements and what additional circuitry is required in order to drive the silicon MOSFETs using this general purpose PWM controllers. Firstly, basing on the market, on the available silicon carbide MOSFETs in the market, they can be categorized into mid voltage, high voltage, and ultra high voltage silicon carbide MOSFETs. For all of these three different VDS rated silicon MOSFETs, silicon carbide MOSFETs, the gate voltage requirements are also different from vendor to vendor. Say for 1700 volt silicon carbide MOSFETs, there are 20 volt VGS gate voltage requirements from different vendors, and a 15 volt gate voltage requirement from the Infineon here. And typically these gate voltage requirements from different vendors depend upon the generation of the silicon carbide. The first generation silicon carbide MOSFETs would need a 20 volt VGS, and the second generation would need somewhere 18 and even 20 for some vendors. And the third generation, the latest generation silicon carbide MOSFETs would need only a 15 volt VGS, which is the Infineon's silicon carbide MOSFET, which is being shown here. Likewise, again, for 1200 volt and mid voltages, there are different voltage requirements: 12 volt, 15 volt for third generation, 18 second generation, and 20 for first generation. So it becomes a bit difficult in order to choose a right PWM controller because of so much difference in the voltage rating, VGS voltage rating from 15 volt to 20 volt. On top of this, the silicon carbide MOSFET on resistance is very sensitive to the gate voltage. So on the extreme left bottom, you could see the on resistance of silicon MOSFET varies drastically with the VGS. So in order to drive the silicon carbide MOSFET efficiently, the PWM controller should have an output which is close to its maximum recommended value, and also the variation in the gate voltage or the output voltage of the controller should be as less as possible in order to drive the SiC MOSFET efficiently. So this is the first and primary requirement for the PWM controller, which is to drive the VGS gate of the silicon carbide MOSFET nearly its at max recommended voltage. And the second requirement is coming from the high zero temperature coefficient of the silicon carbide FET. This is the intrinsic property of the silicon carbide FET. If you see here, here I'm showing the characteristics of a drain to VGS of a ROHM MOSFET, where you could see the zero temperature coefficient hovering around between 14 to 16 volt. This zero temperature coefficient is very important while driving the silicon carbide MOSFET. The reason is if the gate voltage, if silicon carbide MOSFET is supplied with the gate voltage less than this zero temperature coefficient voltage, then the SiC MOSFET can get into this negative temperature coefficient region, during which it can lead to thermal runaway of the silicon carbide MOSFET. This is a cause of reliability, for the silicon for the SiC MOSFET. Hence, all the SiC vendors, SiC MOSFET vendors would recommend driving the SiC MOSFETs with sufficiently high gate voltage, which is higher than the zero temperature coefficient. So this leads to a higher UVLO turn-off threshold from the controller. So the controller has to turn off at sufficiently high voltage when on the VDD. Otherwise, the SiC MOSFET can enter into this negative temperature coefficient region, and in long run, it can lead to the reliability and the damage of the SiC MOSFET. So this is the second requirement, that is higher UVLO turn-off threshold. And the third requirement, which I already said, because there are so many SiC MOSFET vendors out in the market with different VGS ratings, and the maximum being the 20 volt, which is different from the silicon MOSFET, because the silicon MOSFET in these high voltage applications, anywhere between 10 to 15 volt is sufficient enough. But whereas for SiC, it needs at least 20 volt. So the controller VDD also has to be greater than 20 volt. And the last and also very important requirement is the clamp voltage. Because the controller VDD has to be more than 20 volt, but the VGS of the FET itself has to be limited to 20 volt. There needs to be a clamp on the output of the controller. So we'll discuss this more in detail in the preceding slides. So here is the SiC-based aux power supply using, again, the same general purpose PWM controller, UCC28C44. But you would see there are additional components here, external components, in order to drive the SiC MOSFET. When compared to the other schematic which I have shown previously, where there is no need for this additional gate driver or this LDO or this Zener clamp and this UVLO comparator. So let us see one by one what is the functionality of each of these components. Firstly, the external UVLO comparator. So I've been explaining in the previous slide that the SiC MOSFET should have higher VGS voltage, and the output, the gate voltage of the SiC MOSFET should not be less than the thermal runaway zero temperature coefficient voltage. And typically for a 1700 volt MOSFETs, the zero temperature coefficient voltage is between 14 to 16 volt or 15 volt. So the controller should have a UVLO turnoff, which is at 15 volt. Whereas our existing PWM controllers are since designed for a silicon-based MOSFETs, they have a turnoff voltage which is far lower than 15 volt. For example, the UCC28C44 has a turnoff voltage somewhere in the range of 8 to 9 volt, and which is very low for a silicon carbide MOSFET. So that is the reason why an external UVLO comparator is required. And this external UVLO comparator monitors the voltage on the VDD, and if the voltage on the VDD falls below set threshold, in this case it could be a 15 volt, then this UVLO comparator would pull down the the compensator. This is the compensation pin, the compensator pin of the controller, which will stop the switching of the MOSFET. So this is the main functionality of this ULO comparator, to modify the ULO off threshold, which is internally very low, that is 8 to 9 volt of this PWM controller. And second one is the LDO. Since the SiC MOSFET has to be driven with nearly 20 volt, and the UCC28C44 VDD is only rated all the way up to 18 volt, external LDO is required between the auxiliary winding and the controller. So if you want to drive the SiC MOSFET with 20 volt, whereas a controller is only rated all the way up to 18 volt. So what needs to be done is, firstly, this is the auxiliary winding which generates the voltage for the VDD for this controller. And this aux winding has to be designed for a voltage greater than 20 volt. And once this voltage is greater than 20 volt, we bring it down to 20 volt and regulate it at 20 volt, which is the requirement of the gate drive for this, through this LDO. So this LDO brings down the voltage to 20 and regulate it at 20. And this 20 volt now is being supplied to a external gate driver, which can drive this SiC MOSFET at 20 volt. And as far as the power for this controller is concerned, since the VDD is rated only up to 18 volt, an additional Zener diode would be required here to drop this, again, this 20 volt to 15 volt. So this is how we can drive this SiC MOSFET efficiently in this configuration, which is a secondary side regulated configuration with the help of this external gate driver and the external ULO comparator and LDO and a Zener diode. So all of these additional components are necessary in order to drive this SiC MOSFET efficiently and reliably. So here we have given some recommendations on what kind of components needs to be chosen, either for here ULO comparator, TLV2352, and for the LDO, low IQ LDO, sorry, which is a TPS 76901, and a gate driver from TFI UC2705. And this is another configuration. Again, this is a secondary side regulation, but depending on the silicon carbide MOSFET, if the SiC MOSFET, the chosen SiC MOSFET is from second generation MOSFET, which is 18 volt, then a gate voltage which is 18, the output voltage from the controller, which is 18, can be generated without a need for external high voltage gate driver, which is a 20 volt gate drive. So in this case, again, this LDO would be required to drop the voltage coming from the auxiliary winding to 18 volt max, because this 18 volt max is the recommended operating max for the UCC28C44. And then this second generation MOSFET, which is 18 volt rated, can be efficiently driven from the PWM controller without any need for additional gate driver. And the ULO comparator again is required in this case as well, because for the same reason, that is, this MOSFET has to have a higher turn off, ULO turn off. The controller has to have a higher ULO turn off. So this solution what are the advantages and disadvantages of this solution when compared to this? So firstly, in this solution, the advantages are, since this is a secondary side regulated configuration, the voltage accuracy, the output voltage accuracy will be high because we are directly sensing the output voltage. And the second advantage is the third generation silicon, the first generation silicon carbide MOSFET, which is a 20 volt rated, is being efficiently driven with a 20 volt gate drive. And the disadvantages, as obvious, higher system cost and high BOM cost because of so many additional external components. And whereas in this configuration, when using a second generation SiC MOSFET with 18 volt, again, voltage accuracy is pretty high because of secondary side regulation. Still, system cost is high because of the additional external components and the high BOM count. And if although this this configuration is suited for driving the silicon carbide second generation silicon carbide MOSFET, a first generation SiC MOSFET, a 20 volt SiC MOSFET can also be driven, but with 18 volt VGS, which is a suboptimal drive. A third configuration is actually primary side regulation, which is also a bias winding regulation. In this configuration, no external optocoupler is used, whereas the bias winding voltage itself is being sensed and regulated. So since the bias winding voltage itself is being regulated, it is possible to limit this voltage to 18 volt or less than 18 volt, depending upon which generation SiC MOSFET is being used, and no additional external LDO is required. So in the previous case, we were using this LDO in order to regulate the voltage on the VDD. Now, since in this case, the feedback itself is coming from the bias winding, no additional LDO is required. And with appropriate VDD, which is less than 18 volt, only UVLO comparator is required in order to adjust the UVLO turn-off threshold. So the pros and cons of this system, again, no optocoupler is required, so low system cost, but because of the primary side regulation, the output voltage accuracy suffers, which is mainly due to the cross regulation of these windings. And also the maximum VGS that can be given in this scenario is 18 volt. So the first generation SiC MOSFETs cannot be driven all the way up to 20 volt. So these are the three application use cases in which using additional external components and existing general purpose PWM controllers, the silicon MOSFETs can be driven. So the summary: the silicon MOSFETs are not desirable in high voltage aux power supplies due to their poor figure of merit, which is high RDS on and also a high cost. Single switch flyback with SiC MOSFET is the preferred topology for high voltage aux power supplies. Even the cost savings are also appreciable in this single switch flyback topology. The SiC MOSFET allows greater system level benefits like low cost, small size, and high efficiency because of higher switching frequency operation. And the gate drive of the SiC MOSFETs need careful consideration. Since the on resistance of the SiC MOSFET is highly sensitive to the gate voltage, the SiC MOSFETs have to be driven at near their VGS max voltage. And secondly, the turn-off threshold or the ULO turn-off threshold of the controller has to be high enough so that the zero temperature coefficient voltage is less than the turn-off voltage of the controller. And finally, existing general purpose PWM controllers can be used with necessary external components such as the ULO comparator, LDO, and gate driver can be used to drive the SiC MOSFETs reliably and efficiently in high voltage aux power supplies. That's it. Thank you. Now, if you have any questions, please use your chat box and give us the questions.
Very good presentation, Stage. Thank you very much. So now we have around 14 minutes to do the Q&A. As Stage mentioned, please send the question to us. All right. So I get one question from Daniel, and the question is that some SiC MOSFETs require the negative VGS to turn off, right? And how is that accomplished with the TS controller? Stage, could you answer?
Yeah. So the negative turn-off is required for the silicon carbide. That is true, but when being used in the bridge configurations, because in the bridge configuration you have a high side SiC MOSFET and the low side SiC MOSFET, right? And there is a possibility for the potential to turn off of the both MOSFETs at the same time, which is catastrophic. And this can happen because of the dV/dt coupling of the Miller capacitance. In order to avoid this, in the bridge configurations, a negative gate drive is used so that even with the dV/dt coupling, the bottom side MOSFET will not turn on at the same time as a high voltage, the high side MOSFET is turned on. So the negative gate drive is important, yes, but it depends upon the application as well. Whereas in a flyback topology, since it's not a bridge configuration, there's only one silicon carbide MOSFET, which is a low side MOSFET. There is no similar kind of need to have a negative gate drive, because there is a transformer on the top of the silicon carbide MOSFET, right? So there is no potential for a DC bus short.
Okay, thank you, Stage. There's another question that's so relevant. Can the SiC sorry, give me a second. How about the consideration of turning off the switch off? And heard that the SiC FET are sensitive neck VGS. So Stage, maybe I give you some hint that try to mention about how does the negative VGS affect the SiC flyback? Is how does it affect the turn off loss, and or what additional implication from the yes, device performance perspective?
Yeah. So the native gate drive, although is not absolutely required in the silicon in the flyback topology, as I said, right? From the perspective of the shoot through, because there is no chance for a shoot through because of only one silicon carbide FET, right? However, having a negative gate drive is helpful to improve the efficiency of the flyback converter, because having a negative gate drive will help the SiC MOSFET to turn off faster because you have more negative bias, right? And also, typically these SiC MOSFETs have a high internal gate resistance, which would slow down the turn off in case there is no negative gate drive. So for sure, the negative gate drive can help increase the efficiency because it will help to turn off the FET faster. But this is only critical in high power applications, like if you are with a flyback converter, if you're trying to design a high efficiency and high power, like 150 watt power supply, yes, having negative gate drive will help improve the efficiency. And also it would help to push the switching frequency higher because of high efficiency, right? The faster turn on and turn offs. Whereas in aux power supplies, typically these are 10 to 20 watt rated, so not high power, then it is reasonably okay. It's a good trade-off to have not to have the gate drive, negative gate drive.
Okay, thank you, Stage. And here comes the third question. You mentioned that running SiC at a high frequency, and what frequency would you recommend running the SiC MOSFET example you covered?
So these are, when we are talking about aux power supplies, when being driven from 1700 volt bus, a 300 to 400 kilohertz is a max you can run, but typically we would prefer, my recommendation would be 250 kilohertz. Because it's not just the SiC MOSFET, you also need to consider about the transformer and the losses from the transformer when you're driving at high switching frequencies, right? Although SiC MOSFET is capable of switching at high switching frequencies with low losses, but the additional losses through the magnetic components would increase. So the reasonable balance would be a 250 kilohertz.
Okay, thank you, Stage. And another information is that, if for the offline application and then you connect to grid, you need to handle the EMI, right? So in some design consideration will be the less than the 130 kilohertz or 150 kilohertz can reduce the fundamental of the EMI band, and then potentially reduce the EMI. Even though the SiC MOSFET can drive higher frequency due to the nature of the device, but there's some other consideration can be limit the frequency can go higher than that. All right, and the fourth question is this. It seems the SiC MOSFET is not as good as the silicon MOSFET. And do you think that the silicon carbide MOSFET can replace the silicon MOSFET in long run?
I did not quite understand the statement that SiC MOSFET is not good than silicon MOSFET. So I have shown in the first slide, right? SiC MOSFET has several advantages, right? First of all, for higher VDS rating, if you want to go with a single switch solution, with a single switch flyback, then SiC is the only solution, right? With such a high 1700 volt. Although there are few 1500 volt silicon MOSFETs, if you compare the performance in terms of RDS on and junction capacitances and the cost, if you take all the three into considerations, SiC is a clear winner in high voltage applications. Yes, its gate drive requirements are different from the silicon because it needs higher VGS, 20 volt VGS. So we cannot drive directly from existing controllers. So there are some challenges from the controller drive perspective, but the trend is the the silicon carbide vendors or the silicon carbide manufacturers are trying to bring the gate voltage requirements or the gate drive requirements of the SiC MOSFETs to be same as the silicon MOSFETs. And the third generation SiC is the best example, right? They brought down the gate voltage from 20 to 15, right? And now even if they bring it down further, and also they make sure that the gate drive, the zero temperature coefficients are pretty low, then SiC would be a very big impact. It would have very big impact in these high voltage applications.
Okay, thank you, Stage. And an additional thing to echo what the Stage mentioned, you know, we see the customers adopting the SiC FET, even it's not just because of the figure of merit, but also they have no choice. Under this high reflect output voltage flyback together with the bus voltage, the silicon FET, the very minimal options they can take, and the cost of the device is pretty high compared with the SiC. And then if you want to use a lower voltage rating silicon MOSFET, you need to use a cascaded the flyback topology. They will induce additional the cost add up. So from that being said, that we think that the SiC MOSFET, based on what we see so far and the performance we found, we think that there's definitely a place for these high bus voltage applications. And I think in the long run, I think that eventually the overall the device cost will going to gradually drop when this wide bandgap device adopt more and more. So I think that the future trend we see that is very promising for the SiC FET in the aux power application. All right, so Tej, I have the last questions for that remaining 3 minutes. How to know the ability of the driver to deal with the effect of the CGD when the switch on and off, especially in high voltages? From Josh. Sorry.
Can you tell me once again? Can you repeat the question?
Okay, sure. How to know the ability of the driver to deal with the effect of the CGD when the switch on and off? In other words, you know, during the switching node DVDT, there's a middle region, right? So how does that driver deal with this effect? Especially when you have high voltage swing and high DVDT.
Okay, I think this would be more applicable to the isolated gate drivers rather than the general purpose PWM controllers, right? Because in this case, the general purpose PWM controller is in a low voltage domain. Had it been an isolated gate driver, then the common mode CMTI is the specification or the parameter that one has to look into in order to see the effects of the CGD coupling. So for a general purpose PWM controller, I don't see any need for CMTI, common mode transient immunity, whereas for isolated gate drivers, which are used to drive these high side and low side drivers, right? Low side switches through isolation, those needs to be considered for CMTI.
Okay, thanks, Tej. Let me elaborate this additional information here to these questions. And you know, especially for SiC FET, the DVDT is high, right? So to ensure that the switch can turn on and off with known states, that means that the pull down capabilities of the FET of the controller need to be strong enough. So if we take the 28C4X family, the pull down is usually 2 times stronger than the pull up. So that means that when the switch node through high, and then there's the CGD, the charge current from the drain to the gate, so that this low impedance pull down can ensure that there's no additional return on event during that high DVDT event. Okay, so we are right on time. Thank you very much to join these sessions, and also thank you stage of the presentations. So the last thing I want to comment is that all sessions will be recorded and the presentation will be available to view later this week on the ts.com high voltage seminar. And you'll also receive the email and the link on-demand presentation and a post event survey. We definitely would like to have your feedback so that we can continue to improve our content and the future sessions that can eventually benefit for the audience. And thank you again, and have a great rest of your day.